Hi everyone, in this video we are going to cover section 4.10 titled Antiderivatives. Alright, so here we have a new topic, but not really a new topic. Anti at the beginning of the word derivative means the opposite, undoing, taking away a derivative. So normally we differentiate some function with respect to x. Let's say it's x to the third power, and the answer is 3x squared. Right? That's what we've been doing all along. Well, now in this section, we're going to start with the 3x squared and go backwards and figure out what the function is whose derivative is 3x squared. All right? That is called an antiderivative. And here I have it formally defined in maybe slightly confusing notation, but I'll talk about it here. So my function capital F is called the antiderivative of little f if when I take the derivative of capital, I get lowercase. So if I take the derivative of my function and I produce little f, then capital F is called the antiderivative. But what's interesting here is that there are multiple functions. So let's say I have the function x cubed plus 2 and the function x cubed plus 11 and the function x cubed minus pi. All of them have a derivative 3x squared. So the antiderivative of 3x squared can't be each of those three functions, right? So when we take antiderivatives, we're going to write what's called the general form of an antiderivative, and probably like 75% of the time you're going to forget it and be like, oh, well, shoot, I forgot to put the plus c. You'll see what I'm talking about in like a week or two. But what we do to represent that possible constant, 11 pi or 2, is when we take an antiderivative, we're going to write that capital F antiderivative function plus c, where c represents some constant, could be a 2, could be an 11, but it's that constant that is lost when you take the derivative of a function. When you take the derivative of a function, the derivative of a constant is 0. Right? So when we take an antiderivative, we put in a plus c to compensate for that potential lost term. Here, let's look at a couple of quick examples. All right, A, if my function little f is 3x squared, now that should look familiar from the last slide, then I know that capital F of x, the antiderivative, is x to the third power. How do I know that? Well, because I just did it. But what do you get when you take the derivative of x cubed? You get 3x squared. But we also add in the plus c constant. Did you already forget about it? Maybe. So that's the first one. So capital F is x cubed plus c. And antiderivatives are easy to check, or quick to check, maybe not easy, but quick to check because you can just take their derivative. Right now, you're pretty good at taking derivatives, right? Hopefully. So we can always check these antiderivatives with a derivative. B, f of x is 1 over x. The antiderivative of that, well, that one should stand out as being a unique one. We covered it later in chapter 3, right, when we did the section on exponentials and logarithmic functions. The antiderivative of 1 over x. So this is really going to force you to like rack your brains and remember things from chapter 3 and 4 that we've been going through. But the antiderivative is the natural log of x. And we'll see in a chart later on that natural log of x has an absolute value around it. And it's just something that we have to remember to put in there. But the reason why is when I have a function 1 over x, that can be positive or negative. I can take 1 divided by a positive or a negative number. But for natural log, we can only take the natural log of positive numbers. So we have to put the absolute value on there just in case the original function has some negatives in it. Right? But then we add in our plus c. C. F of x is equal to, that's a little f, f of x is equal to the cosine of x. This should stand out to you also. Remember, sine and cosine fluctuate back and forth. You just sometimes get a negative. But right now, capital F, I'm just going to write the sine of x because we remember that those flip back and forth. And to decide if I need a negative in there, right, I'm going to check with a derivative. What is the derivative of the sine of x? Well, it is positive cosine x. So that I don't need a negative sign. It is in fact positive. Plus c. Don't forget the plus c. And then letter D, f of x is equal to e to the x. Well, the derivative of e to the x, do you remember? E to the x. So guess what? The antiderivative of e to the x, also e to the x, but plus c. Now I am going to introduce the language of indefinite integrals. It's what we've been doing in the first part of this video, but it's more formal notation. It's the way that we will typically write this, not with capitals and lower cases. Okay, so the notation here is a long kind of stretched out S. Looks like somebody's trying to draw a snake on their paper. If you're writing on lined paper, it takes roughly the full height of the line. And then we write our function, f of x. And the way that you like read that out loud is the integral of f of x. The integral, that's that sign, that's an integral sign. The integral of f of x, and then we tack a dx on, and that means with respect to x. Because some of you, maybe you're scared of this, but some of you will take Calc 3, and and we will take integrals, antiderivatives of functions in terms of different variables, sometimes 3 at the same time, and it's going to be really awesome. I hope you are really excited for Calc 3. I am. But the dx, that's just what we're taking the integral, the antiderivative, in terms of. It's the variable of integration. That's what it says at the bottom there. Okay, so the integral of f of x dx is equal to that capital F, that antiderivative, plus c. Okay, the integral of f of x dx is the antiderivative plus a constant. All right, the expression, it says at the bottom, f of x is called the integrand. That's not a word that I'll use terribly often, but it's the function that you are integrating. Okay, here is a slide with tons of information on it. All right, so you should pause. You should maybe write down some of these. You should just read through them. It's up to you how you process all of this information, but it's things that the more familiar you are with them, the better off you will be. All right, so up at the top, this is called the power rule for integrals. Right, so if you remember, when I take a derivative, right, if I take the derivative of x to the 5th power, answer is 5x to the 4th. So the exponent comes down and we subtract 1 from the exponent. Well, when I take an antiderivative, right, the opposite, the exponent increases by 1 and the new exponent is in the denominator. All right, so if we check that with our 3x squared that we did earlier, if I add 1 to the exponent, 3x cubed divided by 3, divide by the new exponent, the 3's cancel out, and I get x cubed. Hey, that's how that works. Okay, so switch the process in your brains, like a literal switch here. Add 1 to the exponent, divide by the new exponent, the new one. Okay, and then the rest of this chart just compares. This is what we know about derivatives. Derivative of a constant is 0. This is what it looks like with integrals. The antiderivative of a constant is that constant times x plus c. Okay, the derivative of x to the n, and x to the n minus 1, exponent comes down and subtract. The antiderivative of x to the n, add 1, divide by the new, plus c. We talked about 1 over x a minute ago. E to the x, we saw that in the example. We get our trig function, antiderivatives, and again, there's a lot of information there. Look through it, be familiar with it. This one, make it your new best friend. All right, a couple more properties of integrals, indefinite integrals, and then a couple of examples at the bottom of this slide. All right, so when we have sums and differences, we take the antiderivative of each one individually. All right, that just means that when you have an antiderivative of a sum of functions, right, we just take each term individually, or sum of terms, you look at each term individually. And if I have a constant times a function inside of an antiderivative or an integral, right? That constant just tags along, and we just focus on the x part of it and its antiderivative. So let's use those properties now in looking at these three examples. Letter C is a topic that we did not cover in Chapter 3, so you might see some examples here and there. They shouldn't be on any homework assignments of things that we didn't do in Chapter 3. All right, but for Part A, the integral or antiderivative of 5x cubed minus 7x squared plus 3x plus 4 dx. Okay, so I am going to use the rule up above that says that I can break this apart into a bunch of separate antiderivatives. This is horribly inefficient in terms of how I spend my time, but it's the purpose is that you just key in on the x part of it. So this is the antiderivative, the integral of 5x cubed dx minus the integral of 7x squared dx. The dx tags along. It just tells you what the variable is that you're integrating in terms of, plus the integral of 3x dx plus the integral of 4 dx. Again, very inefficient. I'm not going to, but I could write out one more step where I pull the constants out. Again, that'll take more time than I want to, but that the rule up at the top just says that the constant tags along, and we key in on the x part. X cubed, remember, add 1 to the exponent, divide by the new exponent. Minus 7. X squared, add 1 to the exponent, divide by the new exponent. 3x to the first power, add 1 to the exponent, divide by the new exponent. Plus 4, there is no x there. It's x to the 0. Add 1 to the exponent, x to the first power. If you want, you can divide by the new exponent. The antiderivative of 4 is 4x, okay? Plus our constant, plus c. Let's clean that up a little bit. I'm going to write this as 5/4 x to the 4th minus 7/3 x cubed plus 3 halves x squared plus 4x plus c. And that right there is our antiderivative. For Part B, the way it's printed up at the top looks terrible. Whoops. There we go. So I am going to write it so that it looks a little bit better. This is the antiderivative of x squared plus 4 times the cube root of x, all divided by x dx. Now that looks terrible. No, the rules up above, they don't say anything about fractions. They don't say anything about products. So for now, we're not looking at each of these terms individually because I have this fraction bar here. But what I can do, and you will need to do when it looks a little bit more complicated, is simplify this first. And by that I mean I'm going to take the x and divide it into the x squared and get x to the first power. And I'm going to take the x, the cube root over here, that's just x to the 1/3 power. So I'm going to do that. So this is plus 4 times. If I divide those two x's, subtract the exponents, 1/3 minus 1 is x to the negative 2/3. That's a 3 there. Okay, so we did 1/3 minus the x to the first power in the denominator. All right, so now I see it as a sum of terms. That's much better. Dx. Scroll up and give myself some more space. And our next step is to take the antiderivative. X to the first power becomes x squared divided by 2. Add 1, divide by the new, and plus 4. Even though that's a fraction, I can still do it the same way. X to the negative 2/3 add 1 or add 3/3 is positive 1/3 divided by 1/3. Ooh, that looks ugly. Plus a constant. Final step, x squared over 2 plus, when I clean this up, that divided by 1/3 in the denominator comes up as multiplying by 3. So we get 12x to the 1/3 plus a constant c. And now either of these, a or b, we could certainly check by taking the derivative, and you should get the original function. All right, finally, we have the d that was up there. I had to remind myself what it was. The integral of tangent x, cosine x, dx. C, or no, this is d. The integral, antiderivative, of tan x, cosine x, dx. Now, if you go back in the video or look at OpenStax, that chart that they gave you doesn't have anything for tangent times cosine. I don't know what this antiderivative is off the top of my head. Okay, it's not one that's immediately obvious, but just like letter B, we can clean this up and simplify it first. Well, how do I simplify this? Well, when I have tangents and cosines, that means I have sines and cosines. So the tangent of x is the sine of x over the cosine of x times the other cosine of x that's already there, dx. And when I write it out that way, boom, boom, cosines cancel. Well, all we're integrating is the sine of x dx. So I'm going to just write down cosine of x plus a constant c, and then think really hard, do I need to put a negative sign there or not? Pause the video. You decide for yourself. Do you need a negative sign there? Unpause the video. Maybe you did already. The answer is yes, you do. Negative cosine x, because when I differentiate that, the derivative of cosine is negative sine, so I need the two negatives to cancel out. I really like this visual, and it leads into the last part of the section really well. If I take the integral, the antiderivative of 2x with respect to x, the answer is x squared, because you add 1 to the exponent, divide by the new exponent, plus a constant c. So that constant c can take on any value. It could be positive 2, positive 1, 0, negative 1, or negative 2, or any other value in between or beyond them, right? So when we find these antiderivatives, the result is really this like family of functions, and the family of functions, all of whom have a derivative that is 2x. Okay, so that's visually what we are finding here with our antiderivatives, is this family of functions. But the last part of the section tells us that, like, with just a scotch more information, we can figure out what the actual c is. Okay, and that one additional piece of information is called an initial value or an initial condition. Okay, and so the way that this works is we are given a function, 3x to the negative 2 in this case, and an initial condition. The derivative is 3x squared, but the original value, an initial value on our function, y of 1 is equal to 2. So I have information about the derivative and information about the original function. And so the way that we go through these initial value problems is, all right, if my derivative, dy over dx, is 3x to the negative 2, I want to know what is the original function y, whose derivative is that. If I want to write it formally, I could go the integral of 3x to the negative 2 with respect to x. The constant tags along. The x, we add 1 to the exponent, that's negative 1, and divide by the new exponent, plus our constant c. All right, and then let's write that a little bit better. That's negative 3x to the negative 1 plus c. I'm just doing all this scratch work off to the side. And then I want to write that negative down in the denominator because it'll look nicer. Negative 3 over x plus c. All right, and so that is my original function y. Negative 3 over x plus our constant c. Okay, and we could check that with a derivative. Negative 3x to the negative 1, exponent comes down, subtract 1, you get what we started with. Okay, but now let's bring in this initial condition. Y of 1 is equal to 2. So what that means is that when I substitute 1 in for x, the result is 2, right? That's just a function notation, but with a y instead of an f. Okay, so the 2 goes here, equals negative 3 over the 1 goes there, plus c. Oh, and hey, then we can solve for our constant c. 2 equals negative 3 plus c. Add that 3 to both sides, and we get 5. So that allows me to rewrite my function y equals negative 3 over x plus 5. So we found out what our c value is. Okay, so from the family of functions that is represented by the plus c, we found the one specific function coming from that initial condition. Okay, one really neat, I think, example of that is down here, okay, where we go through a decelerating car example. So pause it if you want to read through the example before I do. But we have a car traveling 88 feet per second. That sounds like a speed, also known as a velocity. The brakes are applied, so 60 miles per hour, but the problem is better when you do it in feet per second. The car, the manufacturer knows that it's decelerating at a constant rate of 15 feet per second, right? The manufacturer of cars would know that. And they want to know how many seconds elapse before the car stops, right? And how far does it travel during that time? Basically, are they going to be able to stop before hitting something in some certain amount of time? Okay, that's what we can answer with those two pieces of information. All right, and the way that we go through it, again, it's kind of cool. I know that the decelerating rate of the car, okay, acceleration, deceleration, I'm going to write this a of t. The acceleration is negative 15, and I'm not going to write the units, but it's negative 15 feet per second squared. Okay, but I also know that acceleration, because we did all this work in earlier sections, acceleration is also the derivative of the velocity function, right? Remember when we had those position, velocity, acceleration examples? The derivative of position is velocity. The derivative of velocity is acceleration. Okay, so if the derivative of velocity is acceleration, that must mean that to get the velocity function, I take the antiderivative of the acceleration function, this time with respect to t. Okay, so if I want to take the antiderivative, the integral of negative 15, well, that's a constant, so my antiderivative is negative 15 times t. Because what's the derivative of 15t? Just 15. Ooh, but we have to put on our plus a constant c. So the velocity of that car is represented by the equation negative 15t plus c. Now with one additional piece of information, hey, I'm circling it up here, we can find out what the constant c is. The initial condition, the v of 0, when we're starting to press the brakes, we are traveling at 88 feet per second. So negative 15 times 0 plus c is equal to 88. 15 times 0, so my constant c in this example is 88. And how did I know to plug in 0, just to make sure that we're clear on that, is because it says when the brakes are applied. That's like the beginning of time in this problem. All right, so I'm going to now rewrite my velocity equation. V of t is negative 15t plus 88. Now I can find out how long before the car stops, because what's going to happen when the car stops? Well, the velocity is going to equal 0, right? That means the car will be not moving anymore. So the car stops when negative 15t plus 88 equals 0. Negative 15t equals negative 88. So that tells me that t is equal to 88 over 15, which in decimal form is about 5.87 when I round to 2 decimal places. So 5.87 seconds, we're solving for t here, seconds, for the car to stop after traveling 60 miles per hour. Okay, that's our answer to part A right there. Part B wants us to do one additional piece. Part B says, how far does the car travel during that time? Well, now I need information about the position of the car. That was S. Position, the derivative of the position function, is our velocity. right? So position derivative is velocity, second derivative is acceleration. We're going backwards through the problem that we've already done. I mean, it's a different application question, but we've already done this in a forwards direction. This is how we do it in a backwards direction to build the function as opposed to being given a function. So our velocity, negative 15t plus 88. I'm going to take the antiderivative of that to get the position function. Negative 15t squared over 2, right, add 1, divide by the new, plus 88t, because the derivative of a constant the derivative of a constant times x is just the constant, right? We've seen that before. And then plus a constant c that we don't know what it is. But technically, we can say, because our starting position in this problem is just the beginning. It doesn't say like we're at the top of a 50-foot tall cliff falling downward. We're just applying the brakes on some horizontal distance. So we can say with reasonable certainty, okay, that s of 0 is 0. And if you substitute that in, that's going to show that c is equal to 0 also. Okay, if you didn't quite follow that, I mean, that's not a huge deal. Okay, I'd rather just you understand the general form of this process. Okay, but the initial position is of the car is 0. All right, so our new s function that we just found, negative 15 over 2 t squared plus 88t. Last step, finally, going back up, how far does the car travel during that time? I want to know what is s of 88 over 15, or 5.87 seconds. Negative 15 halves times that fraction squared plus 88 times that fraction. If you use the 5.87, that's okay also. And then punch it into your calculator. And what are we going to get? This is approximately, oops, I should use my approximately equal to sign, 258.13 feet. So the car takes almost 6 seconds to stop from traveling 60 miles per hour, and it's still, over that length of time, travels 258 feet. That's really important for car manufacturers to think about and figure out in terms of, when they like test braking systems on vehicles. All right, that is the end of the video. Thank you for staying with me to the end. Have a wonderful day.